Thank you. I'm absolutely delighted to be back in Vienna. My first time here was in 2005. That's my daughter. And that was my daughter to me this morning. So that was a more recent picture. I have to say, I looked at this picture and I thought, man, I wish I looked like that now. But anyway, here we are. Pretty much. So what I want to talk about today is joint work with Phil and Debraj. And this is sort of a first step in trying to approach the sort of disconnect between the conditions that we would like to understand, which are typically invariant under changes of metric and biholomorphisms, and the conditions that we actually know how to work with, which typically are not. I'd also like to thank the organizers for inviting me and giving me an opportunity to speak. I'm really thrilled to be back. Okay, so this work most naturally lives in the context of a bounded, really a complex manifold, and I want to start by talking about the d-bar problem on domains omega in M. Let's say we have some fixed Hermitian metric H. We're almost always going to be most concerned about working on a neighborhood that intersects the boundary of our domain, and rho will always be a defining function. And when we have a neighborhood near the boundary, we can always choose an orthonormal basis of 1, 0 forms, omega 1 to omega n, with a dual basis of vectors L1 to Ln. So L1 to Ln minus 1 are tangential, and Ln rho is 1. And this is sort of the setup that I will just assume without, for the rest of the talk. Okay, so for any function, we can write d bar in the usual way. I'll denote the set of increasing Q tuples by curly mathcal IQ, or just IQ. And we can write 0Q forms in the following way, and we have d bar f defined in the way that we've all been doing for a long time. All right, and I'm going to need the notation f sub ji, and this sort of has the standard definition. So if I have a increasing Q tuple j and increasing Q minus 1 tuple I, and an index j, so that as sets j union I is j, then epsilon jij is the sign of the permutation that reorders ji to j and is 0 otherwise. And so f sub ji has this meaning. I'm sure most of us are familiar with this notation, but I don't see any harm in reminding people just in case they're not. So we have, L2 PQ is the space of PQ forms with L2 coefficients. dV is sort of volume form on omega. And our analysis doesn't rely on sort of curvature properties of the manifold. And so for us, there is no harm in taking P equals 0, which is what I'm going to do for the rest of the talk. But our results would apply equally to PQ forms. Okay, I want to use P as a point on the boundary anyway. So d bar is the closure of the Cauchy-Riemann operator that I defined a slide or two ago, and d bar star is the L2 adjoint. And as I'm sure most of us know, if I have a form, 0Q form that's in the domain of d bar star, that will happen if and only if f sub ni is 0 on the boundary. And that's what makes really sort of the L2 adjoint versus the formal adjoint, right? And we're investigating the d-bar problem with estimates. What this means is, given a d-bar closed 0Q plus 1 form f, we would like to find a 0Q form u so that d-bar u equal f, and we have the good, and we want to be able to bound the L2 norm of u in terms of the L2 norm of s. So this estimate here is an example of a closed range estimate, as it's equivalent to the closed range of D. I think calling something a closed range estimate is a somewhat generic term. The kind of closed range estimate that shows up most often in L2 theory, sort of the closed range estimate of this form, where U is in the domain of D bar and D bar star, and HS is the L2 Sobolev space of order S. All right. And when this latter estimate holds, D bar has closed range in 0Q forms and 0Q plus 1 forms. D bar has finite dimensional cohomology, and the inverse to the D bar operator exists. It's called the D bar Neumann operator. So this is the D bar Neumann Laplacian box, and the inverse is a continuous operator. So the motivating questions we have are, when does a closed range estimate hold, and when does D bar have a zero-dimensional cohomology? So there's no cohomology. Okay, so in order to talk about when we can solve D bar, we have to talk about the Levy form. So the Levy form, there are a number of ways to talk about the Levy form. We are actually going to dive in and get our hands dirty, so we really want a very concrete expression for it. So the Levy form is the Hermitian form on T10 given by, L rho xy, dd bar rho xy bar, where x and y are 1, 0 tangent vectors. But with this formulation, certainly L rho depends on the defining function. On the other hand, if R is another defining function, then there is a smooth positive function f defined near the boundary, so that rho is just f times R, in which case L rho is just f times the Levy form with respect to R. What does this mean? So what this means is, if I take a 1, 0 vector x at P, then L rho xx is positive, respectively negative, respectively 0, if and only if LR is positive, respectively negative, respectively 0. This doesn't, however, tell us about sort of eigenvectors and size of eigenvalues. And if we want to talk about eigenvectors of eigenvalues of the Levy form, then once we have a metric, we can define, or given a Hermitian metric H and a form capital H, we can use the musical isomorphism to write the Hermitian form in terms of the metric, and then Hg is a Hermitian operator. And so once you have the Hermitian operator, we can actually talk about the eigenvectors, and we know with our Hermitian matrices, the eigenvalues are real. So once we have a metric, then we can really talk about the eigenvalues and eigenvectors. Okay, and of course, these depend on the metric in a fundamental way. All right, so once we have chosen the defining function and the metric, then we can then we can talk about the eigenvectors and the eigenvalues. One of the things that is independent of both the metric and defining function is the signature. So the signature is just the triple n plus and minus and 0, which is a number of positive, negative, and 0 eigenvalues. Okay? I'm going to need this notation on the next slide. So these, if I have, the omegas as defined on the very early, if I have dd bar u, I can write the ujk's are defined to make this formula true. Okay, so we now assume, in addition, that the gradient of the defining function is 1 on the boundary. And in this case, then we can write down the Levy matrix, so dd bar rho, because the length of the gradient is 1 on the boundary, this is just the conjugate of d bar omega n, and this gives us the rho jk's. And in this notation, the Levy form can be written in terms of components of the Levy matrix. And while the Levy matrix depends on the metric, its signature does not. This is, of course, a point that I'm coming back to repeatedly. Okay, so let's talk about some classic properties of domains. Omega is pseudoconvex, respectively, strictly pseudoconvex if the Levy form has only non-negative eigenvalues for pseudoconvexity, positive eigenvalues for strict pseudoconvexity. Omega satisfies condition ZQ if at every point on the boundary the Levy form has at least n minus q positive or at least q plus 1 negative eigenvalues. All right. Now, these are very classic conditions. The main condition for us that will allow us to run the L2 theory is when the Levy form is Q positive. So what does Q positive mean? So if I have a Hermitian form on an inner product space, we say that HG is when we took H and wrote using the musical isomorphism, wrote it with respect to the metric G. We say that H is Q positive, respectively, strictly Q positive, if the sum of each collection of Q eigenvalues is non-negative, respectively, strictly positive. So the sum of the smallest Q eigenvalues is either non-negative or positive. Okay? Now, I just want to remind you of some very well-known sort of regularity. This is not meant to be exhaustive. This is just conditions that we study when we study the L2 theory of the D-bar problem. Closed range, I've already talked about. And so closed range for D-bar, or equivalently L2 boundedness of the D-bar-Neumann operator, we have this type of closed range estimate. A stronger regularity property would be a compactness estimate. So the D-bar-Neumann operator is compact if and only if this stronger kind of L2 estimate holds. And the best we can ever do in the D-bar problem is 1/2 estimates. And 1/2 estimates hold for D-bar if and only if condition ZQ holds. Okay? So I would imagine most people in the room are very familiar with all of these kinds of estimates. And what I want to point out is closed range, compactness, 1/2 estimates, they're all independent of the metric. Okay? Pseudoconvexity is equivalent to solvability of D-bar in every degree and zero cohomology when it makes sense. ZQ is a condition about the numbers of positive and negative eigenvalues. And in general, when you have conditions that are defined in terms of counting eigenvalues of a given sign, those properties will be independent under changes of metric or biholomorphisms. All right? So, on the other hand, let's talk about what's known about proving some of these things. For example, the most general condition currently for proving closed range of D-bar on 0Q forms is a condition that Phil and I came up with a number of years ago. We called the weak ZQ condition, and it's defined in terms of sums and differences of eigenvalues. For compactness, one of the most well-known conditions, sufficient conditions, is condition PQ. What does this do? This guarantees the existence of a family of uniformly bounded functions, phi m. And what can we say about these phi m's? the sum of the smallest Q eigenvalues, the complex Hessian of phi m is at least m. Many people in this room have worked on compactness problems related to the D-bar-Neumann. So, here is a subset of the names. If I put more names here, if I did all the names, then I would have no room on the slide. And so there's a really natural, there's sort of a basic question here, which is, why is there such a disconnect between the invariant conditions, which are numbers of eigenvalues, and the conditions that we know how to work with, which involve sums and differences of eigenvalues? So what we want to understand are conditions defined in terms of the signature, but what we can prove requires sums and differences of eigenvalues. So where does this come from? Well, if you have sums of, yes, yeah, okay. Yeah, it's certainly not known if property P is invariant under biholomorphisms.
PQ, right?
PQ, yes.
Q greater than,
Yeah, Q strictly greater than 1.
yeah, Q1 is.
Yeah, because that would be about numbers. That would just be about Pluribus harmonic. Yeah. Yes.
Q greater than.
Yeah.
Right. Problem is,
Yes. I mean, my main concern in this talk is Q greater than 1. Okay. I don't think so. No.
I think the problem is,
Yeah.
when you change the metric, even with the relative
Yeah.
size,
Yes.
so it messes up.
Yeah. Yeah. Okay. So where does this come from? So it's actually built into the basic identity. So if you write down the basic identity for 0Q forms, you get, the L2 norm of D bar and D bar star. You have the barred terms, you have the weight term, you have the boundary term, and you have some OK terms. This is assuming that omega is OK, T is large enough, and phi is appropriate. What I'm really most interested in is that we have the sort of the main terms here. And if we go back and look, let's just pick one of these terms and understand it. So the boundary term from the previous slide this is the sum we're looking at. But if you look at some multilinear algebra, like you can find in Emil's book, this sum,
This is not due to me.
oh, I know, I just said it's in your book. So that's the reference for this formulation. Yes. That's why I said it was in your book, not,
Okay.
all right. So, this sum is bigger than m times u squared, where m can be 0 here if you want. That's equivalent to the sum of any q eigenvalues of the Levy form being at least n. So when you do the standard L2 theory, You get sums. That's just built into it, and there's no escaping, okay? So I think that is the origin of why all of these conditions are in terms of sums and differences of eigenvalues, because you can integrate by parts and play around with what you want, but you still are going to have sums and differences, okay? So how can we work with this? Because this is the reality we currently are facing. Well, the idea that Phil DeBrage and I are working on is, well, maybe I can take a condition based on the signature and I can build a metric, and in this metric, I get the conditions about sums and differences, okay? That's the idea that we want to use, okay? Now, we're building a metric, all right? And we're working on zero Q forms. You don't need a pluriharmonic weight function for zero Q forms. You need some function that has to do with sums or differences of Q eigenvalues. So it doesn't really make sense to even work on a Stein manifold, because once you have a strictly pluriharmonic function, then that's somehow asking too much. Also, it doesn't even really make sense to work on a Kähler manifold, because we're going to be building a metric and there's almost 0%. There's no way that the metric we would build would be even Kähler. So there's no point in imposing the extra structure, which we would ultimately not use, okay? So we're just working on a complex manifold with a Hermitian metric. Okay, now a little bit of history. A paper by Andreotti and Vesentini show that there's no D-bar cohomology on Q-complete manifolds at the appropriate form level. They do build a metric to do this, but by the fact that they're working on Q-complete manifolds means they've pushed the boundary out to infinity, and we are sort of most interested in what happens at the boundary. So our techniques have very little to do with what they do. We were, however, very inspired by a paper of McNeil and Verlin from 2015, where they look at the D-bar problem on holomorphic line bundles over domains and Kähler manifolds, and the condition that they work with is this Q positivity condition, which was a strong motivator for us. Okay. So I would remind you, what does it mean? What is Q positivity? It means the eigenvalues are some of the smallest Q eigenvalues are non-negative. And what we first did is we said, okay, given our hypotheses, what's the L2 theory here? This is the L2 theory, and we have some Q fixed between 1 and n minus 1. We're most interested in Q at least 2. And the hypothesis is the Levy form of the boundary is Q positive, and there is a weight function phi, and the complex Hessian of phi is strictly Q positive on omega. In this case, there's no L2 cohomology. Closed range for D-bar was already known in this situation, so the interest is really that there's no L2 cohomology. We weren't going from, in fact, I probably should have just written smooth, because in working with Phil's like, if you say C3, you might as well say C infinity. So he's very dismissive of the C3, and when we actually submit the paper, we probably won't folk. We weren't trying to minimize the regularities. This is just the conditions. Yeah, something that worked. Yeah. We also have another L2 condition here. If we take the Levy form to be strictly Q positive, then we have this should be a 0 here, that there's the L2 cohomology is finite dimensional. The D-bar operator has closed range as soon as Q tilde is at least Q minus 1, and the operator D-bar also satisfies 1/2 estimates. This, of course, is classical because it's just we have a new proof of this. We have a new proof of the result, which is in the spirit of the techniques we're using. Okay, so. So I want to talk about ZQ and Q positivity. At each point of the boundary, of course, the Levy form has, I just want to give you some counting things, but just so you understand, because I'm going to be going back and forth between Q positive and N minus Q. So at each point, the Levy form has N minus 1 eigenvalues. So I'm going to formulate a result that's true for ZQ. It's true for ZQ. I'm just going to talk about the case when we have N minus Q eigenvalues. There's a formulation for the other pieces of the boundary where you have Q plus 1 negative eigenvalues. And so ZQ has, for example, at least N minus Q positive eigenvalues. This means that the Levy form has at most Q minus 1 non-positive eigenvalues, which means that the Qth eigenvalue is then positive, okay? So I want to say that the L2 results, even though they are new, I wouldn't say they're particularly interesting. It's because we just follow sort of the classical techniques and observe that they work in this case. I don't think anybody, I think the reason they hadn't been formulated in the condition we had is because people weren't looking at a problem where this was the setting they wanted to do it, not because there was anything, that's not where the interest is here, okay? It's just we needed to know what the appropriate L2 theory was, so we knew what we had to do in order to make the L2, in order to make our theorems run, okay? So there's a paper by La-Ping Ho from 91 who studies the L2 theory for D bar on domains omega in Cn when the Levy form was Q positive. What's really of interest to us, actually, the heart of the work is to understand how these two matrices interact, okay? And that we'll get to in a little bit. Warm-up problem, ZQ domains, okay? If we can't do the ZQ domain case, then we certainly can't do anything harder. So this is our warm-up problem. And so what we have, what I want to talk about is if omega is a smoothly bounded, relatively compact domain in M, and Q is fixed between 1 and N minus 1, if omega satisfies ZQ, then the L2 cohomology is finite dimensional and the D-bar problem satisfies 1/2 estimates. This, of course, is a classical theorem, and I want to talk about how our approach works for this theorem. Okay, so ZQ has been around for a long time, introduced by Andreotti and Grauert in the 1950s, 60s. Hormander studies the L2 theory for D-bar, and he proved what's necessary to establish the 1/2 estimates on, he proved what is necessary to establish that 1/2 estimates for D-bar and 0Q forms are equivalent to ZQ. That D-bar has finite dimensional cohomology sort of follows fairly easily from these kinds of considerations. Okay. So here's what if we're constructing a metric that's good for a single Hermitian form, this is what we proved. So we have a smooth complex vector bundle of rank D over a smooth manifold M, and S is a smooth Hermitian form E, and at each point SP has at least D minus Q plus 1 positive eigenvalues. And we suppose that there's a closed subset F and a Hermitian metric G naught on M such that on F, the Hermitian form is already what we want. So on F, it's already strictly Q positive with respect to G naught. And what we prove is there is a Hermitian metric G on E such that S is strictly Q positive with respect to G, and in a neighborhood of F, G agrees with G naught. Okay, so we're building a metric where we're taking something about numbers of eigenvalues and getting something about sums of eigenvalues. Okay, now we're going to use this proposition with M is the boundary of omega, the vector bundle is the bundle of T of 1, 0 vectors, S is the Levy form, and D is n minus 1. Okay, and F is a set of points where the Levy form is already strictly Q positive with respect to H. Okay? F could absolutely be the empty set. Yes, that's right. F absolutely could be the empty set. So what's the idea? And the idea is actually, I mean, the devil's in the details, but the idea is actually not that complicated. So let's say at a point P, I write down the eigenvalues of the Levy form, lambda 1 to lambda d in increasing order, with orthonormal eigenvectors x1 to xd. What I would like to do is I would like to, in my new metric, I would like to minimize the importance of the negative eigenvalues. So what's the naive way to do that? Well, if I have, with respect to H, if xj is of length 1, then of course mu xj is of length mu. So what do? So if lambda j is negative, I would take mu large, and then I would take the length of xj to be mu. So what does that mean? That means with respect to my new metric G, 1 over mu x is now a unit eigenvector, and the eigenvalue is now 1 over mu lambda j, right? So we've somehow shrunk them all down. The problem, of course, is eigenvectors are not continuous with respect to your point P. However, if I have some negative eigenvalues over here and some positive eigenvalues over here, the projection onto the set of negative eigenvalues will be real analytic. And so while eigenvectors have terrible continuity properties, projections have very good ones, okay? And so that's the key here. And what we then do is we decompose M where S has a set number of negative eigenvalues, and then we sort of apply this kind of idea sort of iteratively, and that builds a metric, okay? And that's the idea behind the proof, okay? No. Yes. Yeah. But we don't even need real analog. We just need nice enough, right? The moral is eigenvectors bad, projections good, right? Okay. So what we do for ZQ domains, the Levy form has at least n minus q positive eigenvalues. We use the proposition to build a metric under which the Levy form is strictly q positive on the boundary. That's why, yes, it is. That's why we have this inductive procedure that I glossed over. We basically divide the boundary into steps where we know how many positive and negative eigenvalues we have. Yes, absolutely. Yes. That's also why this kind of argument would work for ZQ when we know, but if we wanted to replace positive with non-negative, we'd run into big problems, okay? So this kind of argument, we really need some sort of positivity as opposed to non-negativity, okay? For exactly that kind of reason.
So when you say
Correct. Yeah. Yeah. Absolutely. Yeah. That's why we can't do it in one step. That's why you have to sort of take the piecemeal approach. Okay, so once we have strict Q positivity, then you can use the sort of basic identity in multilinear algebra and get this. So earlier when I said Hormander proved everything you need to prove 1/2 estimates, in Hormander's paper, he has that the L2 norm of F on the boundary is controlled by D bar star, and F. And of course, Hormander didn't write that the L2 norm of the boundary is equivalent to 1/2 estimates. I have no doubt that he knew it. He just didn't finish. He just didn't actually write it down in his paper. Okay, so so our proof provides, I think, a new proof of this result that's very much in the spirit of the metric construction. Okay. All right, so let's talk about what happens when we add in a weight. So if DD bar phi is strictly Q positive on omega or the closure of omega, and the Levy form is Q positive on the boundary, then there's no cohomology at level Q. That was the L2 result that I wrote up earlier. And the problem is, neither condition about DD bar phi being strictly Q positive or the Levy form being Q positive, these conditions aren't invariant. So what we want to do is we now want to move to talk about what happens when we only have numbers of eigenvalues, okay? And so the main result in the paper that the three of us have is the following. So we have M is an n-dimensional complex manifold, and omega C, I think Phil probably wrote this version because C3 is not here. It just says smoothly bounded because C3 might as well be infinity. And we have Q between 1 and n minus 1. And we suppose that there exists a smooth function phi defined in a neighborhood of omega closure so that there is a continuous subbundle of rank n minus q on which both the Levy form and the complex Hessian of phi are positive. And we know that the complex Hessian of phi has at least n minus q plus 1 positive eigenvalues at each point of omega bar. Then there is no L2 cohomology on 0Q forms. The point here is we have to know, the question is like, what's going on with the subbundle? We have to know that where the complex Hessian of phi is positive and where the Levy form is positive, they can't be unrelated to one another. There has to be some interaction between the two of them. Otherwise, there's no hope, okay? Now, in the case that Q equals 1, we removed the continuity assumption on the bundle, okay? So in this case, the analogous statement is at each point P, there is a vector L, and no longer L does not have to depend continuously on P. Just at each point P, there is a vector such that both the Levy form and the complex Hessian are positive. Well, phi is smooth enough and omega is bounded. So, yeah. And the complex Hessian has at least 2 positive eigenvalues at every point. Then the L2 cohomology at level n minus 1 vanishes, right? And the point is there's no continuity assumption on how L varies from point to point. In terms of the numerology here, if Q equals n minus 1, then D minus Q plus 1 is 1. So the common positivity condition is just a vector, right? So it's the same positivity condition just when Q, but appropriate for Q equal n minus 1. Okay. Now, as I said, it is not reasonable to hypothesize there's no relationship between the positivity directions of the Levy form and the complex Hessian. For example, if you were in the horrible situation that the Levy form was negative of the complex Hessian of your wave functions, you really wouldn't expect anything good to happen, right? So that's why you need sort of a hypothesis about a bundle in which they're both positive. Okay. So what we need to do is we need to construct a metric under which the Levy form is Q positive and the complex Hessian is strictly Q positive on omega bar. Okay? So how do we do this? Step one, you build a metric on T10 so that both L and DD bar phi are strictly Q positive. Okay? Our hypothesis will allow us to do this. But this is just on T10 of the boundary. And then from here, you extend to a neighborhood of the boundary and show that there exists a delta so that phi plus delta rho has n minus q plus 1 positive eigenvalues on the boundary, and therefore in a neighborhood of the boundary. And phi we need inside. We don't want to change what happens on the boundary because we like what happens from step 1 and step 2. But once we stay away from the boundary, then we modify phi to incorporate rho near the boundary to preserve the strict Q positivity of rho and phi near the boundary. And we use the metric construction that I already talked about from the ZQ case, the same kind of ideas. We'll build a metric that's good for phi, so phi becomes strictly Q positive away from the boundary. Okay? So it's sort of built up in a sequential way. The key construction, so we have a smooth compact manifold, and E is a smooth complex vector bundle, and V is a continuous subbundle of rank D minus Q plus 1. Let's suppose that Qj is a finite collection of continuous Hermitian forms on E, such that the restriction of each of the Qj's to the subbundle V is positive definite. Then there is a smooth Hermitian metric G on E, such that the form Qj is strictly Q positive. So this is where we go from numbers of eigenvalues to sums of eigenvalues. We use this theorem. S is the boundary, N is 2. Q1 is the Levy form, 2Q is DD bar phi, E is T10 of the boundary, and D is N minus 1, and V is the continuous subbundle of rank N minus Q plus 1 that was hypothesized in the theorem. Okay. In the top degree, the formulation, the reason that the top degree is a little bit easier to work with, and we could remove the continuity assumption, is the positivity conditions just come into the trace and become traces, and traces are just much easier to work with than sort of arbitrary sums of eigenvalues. And so, but this is sort of the analogous formulation of the previous theorem, except at level for the top degree case. Okay. Now that subbundle V that I said we have to have some kind of hypothesis. Well, we actually show if Q is 1, 2, or D, and we have a Hermitian metric such that Q1 and Q2 are Q positive, then there is a subspace V of dimension D minus Q plus 1 on which, so that the restrictions of Q1 and Q2 to V are positive definite. So this hypothesis that there exists a V, I mean, we believe it true for all Q. We just don't have the proof yet. I will say this proposition is a pointwise result and doesn't say anything about the continuity. We don't believe that the continuity is necessary. It's just, it's very hard to get a handle on some of these things without continuity. I'm going to close with a couple of examples. So if n is 1 and q is between 2 and n, so for such an example, we could take Cn minus q plus 1 cross Cpq minus 1. Cn minus q plus 1, we have coordinates z1 to zn minus q plus 1, and we can take phi as you see. And then phi, the exhaustion function, phi is strictly q positive on mnq. And we can't do any better than that because the other coordinates are coming from Cpq minus 1. So here is an example where our hypothesis, the kinds of hypotheses we want are satisfied, and you can't, I'll say, oh, this is actually a Stein manifold that you're just not seeing, okay? If you want a bounded example, then you could just take the unit ball cross Cpq minus 1, and now we then have a bounded smooth exhaustion function that's strictly q positive, the complex Hessian, and there does not exist a C2 function such that the complex Hessian admits n minus q plus 1 positive eigenvalues at every point. Okay? I think I'll stop here.